If I now interpolate a curve in here, it tells me that I'm looking at somewhere about 5.5%. And if I go and plug in a 5.5% and redo our calculations, it is actually going to work. Now you notice what happened here is we started with our MC, right? And it was a magnification on M2. So we started out with a moment of 215, but it got amplified up to 470, right? This is the effect of our P delta effect. Right, so the more slender the column is, the more likely it's going to deflect, and the more amplification we get in our moment. So if I go and change our reinforcing ratio, right now we're at 2.77%, and if I jump that up to 5.5%, what that does is it makes it considerably stiffer. So that means we have a different K value, right? It'll be a much higher K value. In fact, you can see we're up around 1,300 or so, right? So much higher K value. Which in turn is going to increase this value, which in turn is going to increase this value, which in turn will affect this value, and it'll actually decrease it. Right? So what's going to happen is by increasing the reinforcing ratio, yes, this blue curve does move out to encompass the green line, the green point, but at the same time, this green point is going to shift back over here. Right, so the actual reinforcing ratio that we want to target is going to be somewhere between here and here. Right, and so again, this green point, as I increase the stiffness, will move back, and this blue line will shift out. Right, so we want to target somewhere in the middle there. In fact, if I did try a reinforcing ratio of about 5.5% and recalculated it, this point would probably move pretty close to where our blue line is. Right, and then you look at it and you say, well, that's overkill. Let's go back down to 2.77. Right, you find yourself bouncing in between those two numbers. So we're going to target somewhere in the middle here for our next iteration. So I'm going to try 12 30 M bars. So this is going back to our table again here. Looking at our 450 by 450, right, and let's get rid of these guys. We don't need those anymore. Right, so we're somewhere between 5.5% and our 2.77%. Right, there's our 2.77. Right, we don't necessarily want to go up to 5.5 and go overkill on here because we know it's going to change. So somewhere in the middle there. So I'm going to try 12 30 M bars. And that's going to bring us a reinforcing ratio. This is the one we're targeting right here at 4.15%. Right, so not quite up to the 5.5. We know that our point's going to come back a little bit. We could potentially try 3.95, but that one might still work as well. You know, in fact, there's two options for 3.95. So for this one here, we'll get a reinforcing ratio of 4.15%. In this case, because we stuck with 30M, we went from our 2.77 up to 4.15, still within this 30M line. That means we do not change gamma. Right? If I go to a different bar size, like I tried 30M bars, but the next try, say I go down here to 25M bars, then that means gamma is going to change. And depending on where you are, potentially you might end up looking at a different interaction curve. But in this case, we'll stick with the same one so that we don't have any change in there. So what we now do is go back with this value and revise our calculations. So we end up with a new K. So let's bring up our other diagram again here. Our new K then for 4.15 is going to be interpolated, and I'll do this in blue. A new line out here. So there's our new curve. This is our 4.15%. Right, so the curve has shifted out. It hasn't shifted enough to encompass that green dot yet. What's going to happen is the green dot is going to shift back now, so I redo my K calculation. Right, so just as we had before, we were interpolating between 944 and 777. Now I'm going to be interpolating between those two numbers. So Interpolation calculation is pretty much the same here. We just have to redo it. So I'm going to take 4.15 minus 4 divided by 5 minus 4. And the difference between there, 1277 minus that, and then plus that. So same kind of interpolation function that we've been using all along. So here now I get a new k value, and this works out to be 1135. Our BD hasn't changed. This one's still good. So what I do is I go in here for my EI, and I calculate a new value here. So these independent changes here is changing the 906 to 1135. Right, that brings this number up to 3.12. That in turn changes this number and gives us a new PC, 9009. Now we come back over here and change this number here. And that takes this to 315. This value is still good. That doesn't change. So now what we do is we change this value to 315. And it gives us a new value here of 3.46. So now I'm going to take a look and see, again, our PF over AG hasn't changed. Right? This green line across here still remains the same. But now we're down to 3.46, or somewhere around here. And there's our new point there. So you can see how our point has moved back, and now this point lies inside of our new curve. Right, so now we have something that does work. And that's the end of the example. Right, so now we've got a configuration that works. Right, so that's the kind of process that you need to go through for the last question on assignment 4. And again, it's just a matter of I've given you a starting point to try. You go through the calculations, you see where it fits on the curve. If it doesn't work, then you go through and come up with a second guess. And there's more than one guess that's going to work. Right? We just tried one particular guess here, and it ended up being not too bad. We're inside the curve with a little bit of reserve in there, right? So it wasn't too bad of a guess. Again, when you find yourself using the with an example that involves slenderness and having to do that PC or MC calculation in here, right? What happens in here is that I increase the stiffness and it affects PC so the moment decreases. An increase in stiffness will decrease the moment. Right? So again, this point will shift back. Right? So again, what you're looking for is you start with this one, comparing to this curve here, it doesn't work. And the final one that we're looking for is somewhere in the middle. Right? Because as this curve moves out, this line moves back. Right? Now, if you don't have slenderness, that doesn't happen. Right? If you end up with something that's not slenderness, and you take a first guess that is outside the curve, then I can look at this and I can say, okay, well, where does this lie? And I can interpolate a curve in here and say, okay, 5.5%, come up with a new configuration, and I'm good. Right? I don't have to read through the calculations because I'm not adjusting anything other than that curve. Right? The point will remain in exactly the same point. Right? That doesn't move. Right? So it's only because you've got slenderness that this point moves. Okay, any question on that example? Yes?
How does this process change for slenderness if you have reinforcing on two faces?
The process doesn't change. You just end up using a different interaction curve. Right? So there are a whole bunch of interaction curves for reinforcing on 4 faces, reinforcing on 2 faces, and also circular columns, which we never looked at.
So when you were going over in class, you were talking about how like there's a practical limit for I think EI where you get to 6 bars or
Yep.
9 bars. So are we not doing that calculation because that's already encompassed in the K?
That's right. You can actually use those formulas and determine an exact value for K.
Or you can just
Or
use...
here we're just interpolating off the curve.
Okay.
right? So we're using the K values that are directly there. And this is one of the biggest changes that there has been in the concrete design book, the new version versus the previous version, is all these curves have been completely rebuilt. And they all look the same and they operate in the same manner, but the numbers are different. Right? So all of the K values, so look, you go to the old curves, still at 35 MPa and gamma of 0.7, you'll get different values for K, for 1%, 2%, 3%. They rebuilt all of those, so they're all entirely new.
Okay.
Right? And that's one of the biggest changes that we've seen in the